Okay, let's start. So, in the last class, we looked at how to implement common mode feedback. We saw a bunch of variants of them, and finally, we saw how we can use that to make a two-stage Miller compensated OT. Right? Again, we saw the considerations for CMFBs for both the first and second stages. So now, to continue along the discussion, let's now look at how to make a two-stage feed-forward compensated OT. Right? So, can I have the two-stage fully differential amplifier ready? So this is your regular two-stage OTA. Nothing has been done. Now I have to compensate using feed-forward compensation. So let's see how we can do. Right? So again, remember in feed-forward, first of all, let's do this. So let's say I'm looking at differential signals now. Let us say I do plus VID by 2 and minus VID by 2. Of course, this node will be small signal ground. All of this will be small signal ground. So you just have two stages. This is the first stage, second stage. Half circuit will have just two common source amplifiers. That's all. Correct. So first, let me try to draw this at a block level. So let me first draw the first stage here. So I am drawing only for this portion. So here, if what is the sign of the gain from the input here to the output here? Is it positive or negative? The gain from the gate to the drain is negative, right? Inversion. So this is, let us say, some minus GM. Same is the case for the second stage. That is also a minus GM. Now I want to compensate using feed-forward compensation. So what do I do? Here, what do I do? Okay, you forgot feed-forward compensation already. What do I do for compensating? We add one more GM. So let us say I add here. So what should be the sign of this GM here? Positive or negative? Positive. Why? Yeah, you get the idea. We should the zero we introduced should be in the left half S plane. So the two parts that add to the output that introduce zero should have the same signs. Right? So this has a positive sign. This should also have the positive sign. So at a block level, this is what we are supposed to do. Let's try to implement it here. So let me remove all these things. What relevant now? So let me call this Vi plus VIP and Vi minus, and these are my final outputs. Right? Now all I have to do is sense the input and push in a current at the output. Right? So here I have a differential input, so I have to sense a differential input and pump in a current corresponding to that. So how do I do that? What can I use to convert this differential input to a current, differential current? OTA. I mean, so how do I make it? What is the simplest way to make it? I mean, the question clear. All I have to do is basically sense the difference between the two voltages, convert into a current, and push the current at the output. That's what I'm doing here. So I'm asking, how are you going to make it in circuit? Pi trans OTA. I mean, even the fundamental thing is this diff pair. Correct. This is what is taking the voltage and converting it to a current. So let me try to draw it here. So you have one more differential pair here. That is a feed-forward OTA. Okay. Now I'll basically go and connect it here. Right. Now the question is whether this should be the positive or this should be the positive input. How do you find it? That is the question is whether should I have the positive input here or here? Left side or the right side? How will you find it now? How will you find it? Give me some feedback. Okay, first of all, can I connect it randomly here? Can I connect, I toss a coin and randomly put the APVM here, or what should be the considerations I should have in mind?
Both parts should have same current.
Both parts should have? Same thing you did here. What's the confusion, right? So then how will you find out what is the correct thing to do? Yeah, what you told is correct. Both the currents here should add in the same polarity. How will you find out then what should be the input here? I mean, at a block level, how did you figure out whether this is plus or minus? Huh? Sorry? Okay, first of all, tell me how did you conclude that this is plus? If I'm saying that this should be minus, prove me wrong. Forget about the circuit. At a block level, how did you say that this was minus? Huh? Correct. So, yeah, okay. So, yeah, that's all correct. But how did you figure out this is negative? I mean, this is positive. Yeah, current direction, yes, but that doesn't mean. I mean, you're saying sun rises in the east. I'm brushing up in the morning. Those two are events, but there is no correlation, right? I mean, sorry. Sure. Okay. So sure. Assume V in. Okay. So then. Yeah. Let us say current is outside, so which means the voltage here will be positive or negative. Negative. So what should be what will happen here? So now how will you figure out this should be positive or negative? These two must have the same signs. So what should be the sign of this? So now tell me how will you figure out here? I'm saying that here I have applied VIP VIM. I'm asking what should come here. Okay, let's increase VIP. So which means VIM is reducing. What happens to this voltage? Decreases and increases. So let me call this as VO. This is decreasing, so I'll call it VO minus 1, VO plus 1. Fine. So then what will happen to this voltage? This voltage will decrease. Correct. So now tell me this voltage here is increasing. So which means here I should connect the negative input or the positive input? Negative or positive? Yeah, because from here to here there is a sign inversion. So which means here what should I connect? Is that clear? So here I'll go and connect the minus input. Here I connect the plus input. Is it okay? So I'll redraw this in a slightly more visually appealing way. So let me see if I can reduce the size here. I'll keep it here for reference. So first let me draw the first stage. So this is the first stage. So let me label this VI plus, VI minus. At the drain, this is VO minus 1, VO plus 1. Okay. So now what I am doing is I am having the second stage. So let me see if I can reduce the size of this further. Space. Yeah. So I'll draw the second stage here. So assume that this is taking VO plus 1. This is taking VO minus 1. And then you have the current source here. And this is going to be VO minus. I've just drawn the two-stage OTA slightly differently, that's all. This okay? Now I'm adding the feed-forward path. So let me add that. I'll erase this. So feed-forward path, we are adding it here. So if this is the negative output, so here I should have the negative input or positive input. Positive input, right? Because I should have the same signs both in this path as well as in this path. So here I know that this is my minus output, so which means for the chosen inputs the output here is reducing. So here I have Vi plus. So now one quick question. So here I added the feed forward OTA using this diff pair like this. So can I not have the tail current source and then just say that I'll have a pseudo differential case like this? So what is the difference between doing this versus having an extra tail current source? When we looked at fully differential amplifiers, we saw two cases. One was doing like this and one was adding this tail current source. What is the difference between the two? The common mode, yeah, basically if you have a pseudo differential implementation like this, even if you have a common mode excitation, the output will respond to the common mode excitation, correct? Of course differentially it gets cancelled, but we saw that any common mode excitation will result in a response here. So you want to avoid that, so it is better you have the tail current source here, because remember that at the input side you had this tail current source and try to suppress the common mode inputs, common mode changes. But if you don't have the tail current source here, the same input is given to these fellows also, so any common mode change will kind of disturb the output here, right? So make sure that you have common mode rejection here also. And in general, if you have a multi-state structure like this, let us say A1, A2 something, right? So it's always better to have common mode rejection for both of them, but if not, it is important to have common mode rejection for the first stage at least. That way any common mode changes you have at the input, this will suppress, and then since here there is not going to be any common mode changes, here even if it's pseudo differential, it's okay. But any stage that is processing the input, you make sure that is having a good common mode rejection. So now this can be further simplified. So let me call the bias current for this transistor to be some I4 something, and or maybe I'll not call this here, and I'll call the current here to be some I6, not here. I'll call this current to be I6. So what can you say about the DC bias current in the NMOS transistor here? How much? I4 minus I6, right? Now tell me what might be a trivial design choice for I4 and I6. If you want to simplify the circuit further, what can you choose for I4 and I6? Yeah, same. So what will change? What will reduce now? So what will happen to this current then? 0. So then do you need these transistors? Correct. So this way you can reuse the same current for the second stage and for the feed forward stage. Okay. So that is a common choice that is done to save current. So what is done is the following. You choose the same current for the second stage here as well as for the feed forward stage here, which means 0 current flows in this current, this transistor. So I can potentially remove this. So basically I'll have something like this. So this again I can neatly redraw it like this. This is Vi plus. This is Vi minus. And the tail current source I'll show with an NMOS transistor. So this often is referred to as current reuse feed forward OTA. For obvious reasons, because we are reusing the same bias current for the second stage here and the feed forward to save current. So this is how a two-stage feed-forward OTA will look like. A common implementation will look like this. And of course here, remember a differential mode, yes, we have made sure things are fine. But what can you say about the common mode voltage here? Will it be set? If I just don't do anything and just have this alone, this is the common mode voltage for here defined. So what should you have? Should have a common mode feedback. Again, same considerations we saw for two states, similar considerations will hold good. Let me just show it and then we'll wrap up. So let me push it here. So basically you need to have a CMFB for this fellow. So this fellow will sense the common mode of VOM and VOP. What is the common mode of the two voltages, VOM and VOP? If I have two voltages, VOM1, VOP1, what is their common mode? Basically, it senses this common mode and makes sure that it is equal to a required reference you want. And then you can go and tune this PMOS curve. Same thing we saw. Similarly, even for the second stage here, you have to have a common mode feedback, because here again, this voltage will not be defined. So once again, you need to have a CMFB. Maybe I'll just show it once. So maybe you have a resistive thing here. You take the average, compare it with the reference, VCM ref 2, and then here, what is the current source I can go and change, tune? Only this, right? Because this is basically fixed for you, because the output common mode here is set by this CMFB stage. So that will decide the bias voltage here. So this PMOS current is automatically fixed for you. The only thing you can change to stabilize this output bias or common mode is this transistor. So you go and basically, maybe I'll flip it and draw. Or it's okay. Yeah. Do something like this. Now again, remember when I do this for the second stage CMFB, I have one OTA here. The input is given to the gate of this transistor and the output is tapped from here. So once again, you have a two-stage OTA. So what is the simplest way to compensate this CMFB loop? Miller capacitor. So maybe I'll draw the common mode equivalent, then it becomes easy to visualize. So only for common mode, if I were to draw this for the second stage, I'll remove the first stage. So second stage, if I draw the common mode half circuit, so this is what I had. So both voltages will be equal. So both these voltages will be equal. So I'll show only one half like this. This is what I'll roughly have. So this is the first stage. This is the second stage. So remember, the input to the second stage is here and the output to the second stage is here. So if I were to do Miller compensation, where will I put the capacitor now? Across second stage, but exactly, okay, I'll put one capacitor here. I mean, the one end of the capacitor is connected here. Where should the other end be connected to? Huh? Yeah, I mean, should I connect it here, here, or here? I mean, lower, middle, upper. Which birth? Middle? Why? Yeah, remember, we should across the second stage is where you are supposed to put the capacitor. Input to the second stage is here, whereas the final output is here. Right? So you basically go and put the capacitor. So again, this is only in the common mode picture. So in the actual circuit, let's see how we are going to do. So again, remember, we are going to put the capacitor from the gate here to this final output. Right? So here I have two outputs, one gate. So how will the capacitor now be connected? In the common mode half circuit, I just had one single capacitor, let us say some CCM, connected from this node to the gate here. So in the actual circuit, how should the capacitor be connected? I should have two capacitors. So obviously one end is connected to the gate. Let me put it here. Where should the other end be connected to? I have two outputs. So I'll basically have one capacitor connected like this, another capacitor connected like this. This is how it's going to look like. And again, if I were to redraw this in a better way, what is typically done is this, just for the sake of drawing or showing it, I'll assume that this current source is split into two halves. The single transistor is split as two halves. So which means, I can say one goes here. Okay. Yeah.
Sir, the current source of the first block, that is right.
This one.
That is driven by outside.
Yeah, you'll have some biasing. You have to bias this properly. Yeah.
Can't we just leave that biasing for the other and assume it to be stable?
No, it is not, because this voltage is not stable. So if I don't do CMFB, and where did I have this schematic? Let us say I don't do any kind of CMFB and then directly bias this to some voltage. What is the problem? I can connect to any voltage, right? What is the problem? Remember, again, this is one current source pushing some current, this is another current source pushing some current. They will not be equal. That's the whole point, right? It is not because this voltage is not stable. The issue is you can't have two current sources connected in series because the intermediate node is not defined. That's the whole reason for having this entire loop, right? This is basically going back to your common source simple transistor biasing, right? I can't put a current source and then say that, hey, my gate voltage and will be set automatically. This is again saying that switching on the switch and fan turning on, right? There should be some kind of feedback, because here again you have same thing, right? This is one current source, this is another current source, right? So there should be some feedback to set this voltage, and that's what here we are doing. An extension is this common mode feedback. No big difference. So any other questions? First of all, is it clear why we are doing this common mode feedback? Yeah.
I didn't understood why we are putting the remainder in this stage. Why not in the first stage or somewhere?
Where do you want me to put? We can suggest. What is your suggestion? Let us say I'll go to the common mode half circuit. Or do we not have the common mode half circuit? This is the common mode half circuit, right? Yeah. So where would you want to put?
So basically, this one is second stage and that one is third stage, right?
Sorry. Yeah. This is like the second stage. This is like the first stage. Yeah. This basically I gave a problem also actually. If you have two GMs, GM1, GM2, right? So finally, if you put it in feedback, it is it's not possible to say what is the first stage, what is second stage, because it is in feedback, right? I can draw it in both ways. In fact, this was one of your practice problem sets. I can think of it like this, or vice versa, right? I can think of it the other way also. I can think GM2 is this and GM1 is coming here. Now the question is, you are going to put a capacitor here. Basically, if you put a capacitor here or if you put a capacitor here, both will be same, right? Finally, the capacitor is put between these two nodes. Now whether you in the actual thing you put it here or here, moment it is in feedback, it is going to be same. But the question is, what is the right thing to do? Okay, so in fact I gave it as a problem, and I actually in one of the practice sets, okay, can go. I'll let you figure it out. But at least, does it make sense? Now we can think of it as this as the first stage, this as second stage. Typically we put it across second stage, so that's where the capacitor comes here. And in practice, another modification you can see is this. So here, in this circuit, I have common mode rejection only for the first stage and the feed forward stage. So let us say you want to have a common mode rejection for the second stage also. Then you can go and put a tail current source for here. which means now even the second stage, this is the second stage, remember, even this will have a good common mode rejection. And once now if you have this current source, now your CMFB can basically tune either this current source or this current source. Now we have option. Earlier when I didn't have this tail current source, the current here was decided by the common mode here, whereas now this current source is now free to tune. So we have a PMOS current source and NMOS current source, so we can fix one of them and tune the other. So that's like how here I have fixed, in this particular scenario, I've basically fixed the PMOS current source and tuned the NMOS. I can also do the other way around. I'll say that the NMOS current is fixed and go and tune the PMOS current source and then put all the compensation properly for it. Right? So we'll have the same thing here. Either of them will work. So if you were to clearly show, this is your first stage. This is stage number 1. So this is your, where will I write it? This is your stage number 2, and the green portion is your feed forward stage. Any questions on this? Is it okay? Cool. So then I just want to mention about another thing about CMFB. So again, let's get back to the first point of discussion. So let us say I had a normal fully differential amplifier like this. So let me consider a pseudo differential amplifier. So this is a pseudo differential implementation. So here again, what is lacking compared to a fully differential case? Yeah, correct. But finally, what property this one? Because there is no tail current source, what happens here? Yeah. So which means if I apply any kind of common mode input here, the outputs will respond to that. If I draw the common mode half circuit, I just have one half. Correct. This is the common mode half circuit. So which means if I apply any small signal VIC here, what will be the small signal output here? If I call this say M2, M4. If the small signal input is VIC, what is the output? Yeah, what is the gain? Yeah, minus GM2 times. Yeah, so let me, if I were to write it clearly, the short circuit GM in this case is how much? GM2 or plus GM2 or minus GM2? What is the output resistance? R0 4 parallel R0, correct? So which means, let us say I apply a common mode step jump. This is your VIC. Okay. So which means, what will happen to the output now? The output common mode. Let us say it's starting from 0, small signals. From here, what will it happen? Sorry? I mean, what I'm saying is, if I apply a small signal step here at the input, what will happen at the output? Step up or down? Down. By that much gain, right? This gain, GM times R out gain. Okay. But let us say I even try to make a pseudo differential amplifier like this. So even in this case, do you think the output common mode bias is set properly? I have a PMOS current source, NMOS current source sitting happily without anything. So here again, you will not have any, common mode is not defined. So what you should have here? Should have a common mode feedback here also. So let's say that you have some common mode feedback. So let us say the same usual thing. So I have a resistive common mode detector. and then I compare it. So I'll basically go and control, correct. So in this case, let's see what's going to happen, because this is the most practical scenario, right? Because without CMFB you can't use the circuit, even the pseudo differential. So after adding the CMFB, let's see what's going to happen. So here in the common mode half circuit, I'm going to have a resistor, a GM, right? These two will be put in parallel, so this becomes a single resistor, and then I have the OTA and feedback. And let me look at small signal. So this is grounded, so this also grounded. Again, this is my output common mode, VOC. So now tell me, do you think the short circuit GM is different or same here in this new circuit? Will be different or same? How will you find the short circuit GM in the circuit? Huh? Yeah, if I short the output and find the current, do you think the current will be different or same? Same. I mean, the moment you short this fellow is not active at all. So I mean, should make sense, because this is the transistor that's doing the conversion. So this is same. But what do you think happens to the output resistance now? Yeah, what is the output resistance? Can you look and tell me? For example, let us say this has some, assume that this has a DC gain of some A1. Does it does it remind you of something? Gain boosting. So you basically, I mean, remember that if you had a simple gate to drain connection, what is the resistance? I mean, in this case, what is the looking in resistance? By GM. So here what we have, I am not connecting the gate and drain directly. From the drain I have an amplifier. Yeah, something. So this is basically, you know already, this is 1 GM times A plus 1. Correct, same thing. So let me write it directly. So R out has become from this value to 1 by roughly A1 times GM4. So which means the moment I add a common mode feedback, earlier, let us say without the CMFB, the output common mode went from small signal output common mode went from 0 to this large value minus GM2 times R02 parallel R04. Now, what is the value to which it will reach? What is the gain now? I mean, short circuit GM is this, R out is this. What is the gain? Minus GM2 into this fellow. Assume that GMs are roughly equal. So it's basically of the order of 1 by gain of this amplifier. So do you think this jump now will be smaller or larger? This will be much smaller, right? So basically be much smaller. If the gain is really large, this is actually going to suppress it. And ideally you want to have a really large gain here, so that the output common mode is defined to the required value. Right? This is not grounded. This is connected to some VCM ref. So which means now it seems like even in a pseudo differential case, the moment I have a common mode feedback, the CMFB is helping me suppress any changes in my input common mode. Correct? Does it make sense? Earlier, one of the reasons I mentioned for against pseudo differential was it does respond to common mode inputs. Whereas now I see that if I have a CMFB, which is what you have to use, looks like this jump is basically suppressed a lot. So that begs a question, then why do you need to have a fully differential case by putting a tail current source? For that, let's look at this in slightly more detail. Now remember, here I just assume that it's all DC. I didn't consider any capacitor. But of course in practice you are going to have parasitic capacitors. So let us say I assume a load capacitor here, something, or I'll call it C1. Here also I'll have some capacitor, something. Okay. So if I have capacitor now, let me erase this. Okay, let me have it. Yeah. If I have the capacitors now, do you think if I apply a step, the output will instantaneously jump like this? Because you have capacitors, this feedback loop cannot respond instantly. It will take some time. So initially, let us say this loop is not active, which means it is as though this loop is not present. Correct? Just after you apply the step, this loop is not going to instantaneously respond. So which means initially, if I apply the step, what is the current that is drawn here? Small signal current. In this direction, what is the small signal current? The gate voltage is VIC. What is the small signal current? So this current is always GM2 VIC, right? No confusions. Okay. Now at t equal to 0 plus, since this loop is not going to respond, we have this current getting drawn out of the capacitor. So what will happen to the node voltage here? I have a current GM2 VIC getting drawn from the capacitor. So the voltage will reduce, right? So basically now it will try to reduce. And what is the, let us say this current is constant and you just have capacitor. What is the slope at which the voltage will drop here? I have a current I getting drawn out from a capacitor C. What is the rate at which the voltage will drop? I by C. So basically the slope here will be GM2 by C1 times VIC. Now this won't happen all the time because after some point the loop will start to respond. Then the loop will try to make sure that this voltage doesn't keep going up like this. Eventually it should basically settle to this value. Now depending on the stability of the loop, if the loop is nicely stable, it might instantaneously or it might quickly do this. Or if the loop is not stable, maybe it might ring and settle. Or if the loop is not at all stable, then it will basically keep doing this. So now you see that, oops, let it go. Yeah. In presence of delays in the loop, even though the CMFB eventually is trying to make the output, let me erase this. Yeah, even though the CMFB is eventually trying to make the suppress the changes in the output common mode, because finally it is making the output common mode equal to this reference value. So small signal change should be 0 ideally, but although it's trying to do it in steady state, in transients you cannot guarantee it. You can have a large common mode variations. So now how fast this loop brings it to the final value, that is determined by the omega u loop of the common mode. The unity loop gain frequency of the common mode will determine how quickly this is basically able to set it to the actual final value, right? If the loop is very slow, then maybe the common mode can go so much and then come here. But if the loop is very fast, what can happen is it can instantaneously push it like this, right? It can just go only so much and instantaneously bring it back. And of course, the phase margin of this common mode loop determines whether you have a lot of ringing or less ringing, or how is it settling. Is it okay? So that's a takeaway. Even though you have common mode rejection provided by the CMFB loop, it is okay. It is valid for steady state, but in transients you can see actually depending on the speed of the common mode feedback loop, you can actually see large changes in your output common mode. Now let's actually quickly compare it with what happens if you have the tail current source also, so that we know how that is better. So I have a tail current source. The only change I'll have is this: go and put a current source here. So how will the common mode half circuit change? So here I have the transistor. If it's an ideal current source, what will come here? Sorry, it's an open circuit. So in the common mode small signal equivalent circuit, because you have an ideal current source, this is open. So now let's calculate the short circuit GM and RO. Now again, do you think the output resistance will change? No, let's look at only DC, capacitors for now. Output resistance will not change because the same thing you have. What can you say about short circuit GM? Let us say you short the output, you apply an input. What will be the small signal current flowing? 0. So what's the short circuit GM? Right. So now you see that even if you have delays in the loop, you have capacitor, you apply a small signal step, but what is the current flowing? So which means will the output common mode change? So which means here it will basically not change at all. Now, of course, this is an idealistic case, but let us say you have not an ideal current source, but a practical current source with a large output resistance. So let us say this is a very large resistor Rx. In that case, if I call this voltage VIC, approximately what is this voltage? Input at the gate, output from here, the resistance is very large. What is this voltage approximately? VIC. So now what is the current flowing now? No, I mean this voltage is VIC. What is the current then? So the small signal current flowing here is, so if the current source is not ideal, it's roughly VIC by the resistance, and the resistance is infinity, the current is 0. Correct? So which means earlier your output was doing all this and going, because earlier the output current was large, GM2 times VIC. But now you see that the output current, or the common mode current that we are pushing is much smaller. So which means the output might actually not rise so much, it might be very small change. So that's the advantage of having this tail current source. So if you have a common mode rejection in your circuit to begin with, in the form of having a tail current source, that first of all reduces the short circuit GM for common mode signals. So that way the common mode currents getting pushed into the output is going to be really small. So even if there is a delay in the common mode feedback loop, your output common mode will not change a lot. So that is why in practice we prefer doing this, because this gives a first level of security. Now the CMFB provides a second level of security against common mode jumps. Is the point clear? And other thing to observe is, the moment I had the common mode feedback, right, you see that the output resistance actually reduced a lot. And it should not be surprising, because here we are having a negative feedback loop. So here this feedback loop, it is trying to sense a voltage quantity or a current quantity. Voltage quantity. At the output, it is trying to keep a current constant or a voltage constant. At the output, it is trying to keep what equal to what? I mean, the feedback loop is trying to keep what quantity equal to what quantity? This VOCM equal to? So the output is a voltage quantity or current quantity? Voltage. And we are sensing voltage or current here. So what kind of feedback loop is it? Voltage or voltage current? Which means it is trying to mimic what kind of a control source? Voltage control? So this is basically trying to make this into a better voltage control voltage source. So what can you say about the output resistance? Will be smaller or larger? It's a voltage source at the output, so the output resistance will decrease. So that's why here also you see that the output resistance actually is decreasing. So these are the two things to have in mind, that when you have a common mode feedback loop, because it is trying to form a voltage feedback like this, the output resistance for common mode signals will be very small, because what we have checked is only for the common mode half circuit, right? The differential mode half circuit, this will not come into play, right? Because the differential mode half circuit, this point is going to be grounded, so the OTA will not come into play. So to summarize, the act of using a common mode feedback, because it is making a voltage feedback, it reduces the output resistance for common mode signals. So in a way that helps you make sure that the common mode gain is much smaller, but it doesn't do anything to your short circuit GM. To reduce the short circuit GM for common mode signals, you need to have this tail current source, that will provide an additional layer of protection against common mode variations. So which means in this case, the common mode current getting pushed in is going to be much smaller. So if you apply any changes at the input common mode, the change at the output common mode will be negligibly small. So that is why it's preferred to have both of these at the same time. And as I already mentioned, it is very important to have this common mode rejection, at least for the first stage. If you have multiple stages, it is very important that the stage processing the input signals, if I call it Vi plus Vi minus, the stage processing the input signals must definitely have a tail current source to give common mode rejection. Okay. Any questions? So let me just remark it here. So CMFB basically reduces the output resistance for common mode signals. That's the important thing. So which means the common mode gain is going to be smaller, but this is only at DC. So that summarizes the things I wanted to explain about common mode feedback. So any questions on this so far? So we'll move away from common mode feedback. So hope it is clear. Okay. So then let's move on.